Okay, now to start with, we've already talked about circular orbits. And we could figure out what are the conditions of a perfect circular orbit, let's say, around the Earth. And as you know, we have a whole bunch of artificial satellites that are up there, and their typical orbital period is about 90 minutes. So if these are the values for the gravitation constant and the mass of the Earth, figure out, or at least set up for a few minutes, what's the radius of the orbit? Okay, so set that one up for a couple of minutes, and then we'll work it out and see what we get. So what are we trying to find? Radius, and we have, what do we have? Period. So what should we use for the acceleration? So could we have v squared over r? We have omega squared r. Which would be more useful?
Omega squared r.
Probably omega squared r. Okay, so let's see. M omega squared r is equal to g m over r squared. I'm trying to solve for r, so I'd like to throw the other junk to the other side. So I'm going to get r cubed is equal to g m. The little mass goes out. And let's see, omega is, what, 2 pi over the period that I have to put at the bottom and square. So that looks like g m t squared over 4 pi squared. So let's see what that works out to be. I suppose I should take a cube root, so the actual radius will be g m t squared 4 pi squared raised to the 1/3 power. All right, so that's going to be a lot of numbers, so we're going to start over here. R is equal to 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Oh, that's too high. Epic fail. All right, move that down. Mass of the Earth, 5.97 times 10 to the 24 kilograms. T squared, so that's 90 minutes, too high still, too bad, 90 minutes squared. Over just 4 pi squared. And raised to the 1/3. All right, so let me check my dimensions. I guess I'm going to have to convert the minutes squared into seconds squared. So, okay, the numbers, bits, 6.67 times 5.97 times, let's see, 9 squared is 81. And 60 seconds in a minute, so that's going to be a 36. And now let me pick up my powers of 10. Oh, is this too complicated? Fine, all right. So 8,100 minutes squared. And then I have to multiply by 3,600 seconds squared per minute squared. Do you agree with that? There's 60 seconds in a minute. You're nervous. you're less nervous, okay? That's good. Okay, and I need to put over 4 pi squared. I need to pick up my powers of 10. Negative 11 and 24, that makes 13. Okay, and I need to pick up my units, so I have Newton meters squared per kilogram squared, except that I have 1 kilogram there, so that's going to be Newton meters squared per kilogram, and I'm going to end up with seconds squared in there. Okay, so let me make sure I got units that are going to work out. So I will have Newton. What's a Newton? Kilogram meter per second squared. Okay, so we'll write that in. Kilogram meter per second squared times meters squared over kilograms times seconds squared. Okay, so the seconds go out. Oh, that's nice. So I get meters cubed. And if we run all the numbers, presto changeo, somebody have a calculator, I think we get 6.65 times 10 to the 6 meters. Or 6,650 kilometers. So how high up is that? Remember, what's the radius of the Earth? Radius of the Earth is about 6,380 kilometers. So how high up are these satellites? Oh, not very high, right? That's about 270 kilometers. How far is that? So these low Earth satellites orbit in about an hour and a half, and they are only about 140 or less miles up. Just out far enough so that there's no appreciable drag from the atmosphere as they go around.